Hello YouTube, so today's video is going to be about this circuit right here. So in a previous video I mentioned about either one of these circuits, which is a full adder, a binary adder circuit made out of discrete transistors. Shown here is 8 of these binary adders wired up to create a ripple carry adder. Ignore these circuits at the bottom, these are XOR gates. They are not wired up right now, but if they were, they would be used to allow subtraction using 2's complement. But how we have it just here, it can just add binary numbers. So you can see how it does that is that it's adding 2 numbers, A plus B equals the output C or whatever. So in this situation, A would be yellow, B would be orange, and the output, the sum, is this right here, the blue wire. And of course you could see that all of the oranges go together and all of the yellows go together. That's because each has 8 bits. And they go to the switch right here. So of course these are your 2 numbers, A and B, and you could add them together and produce an output. The output it goes from these blue wires out here to these LEDs. You can see that there are 8 LEDs for 8 bits. Just to demonstrate this, so we could have it right here. And if you don't know how the binary works, it's 1, 2, 4, 8, 16, 32, 64, and 128. This is just 8 bits. You could go up to many more than that. You could go as much as you want, but you'd have to add more of these. And of course, there are other ways to make binary adders. The ripple carry adder is the simplest one, but it does have the disadvantage of that the additions have to happen at the first one before they happen at the 7th one right here, or the 8th one. You do that using a carry look-ahead adder, which involves more circuitry rather than just wires together. But how we have it here, it's rather simple. You could do 1 plus 1 is 2, imagine that. And then we could have 2 plus 2 is 4, well, imagine that as well. And of course we could keep going up. You say whatever this one is plus whatever this one is 32. So 16 plus 16 is 32, yeah, sure. And then here's something interesting. Since we only have 8 of these and we have 8 of these, well, let's say what we do is the last one plus the last one is overflow. So it goes to 0. Well, you might be wondering what happens with that. And you could see right here that you could see that the purple is carry out, green is carry in. So the carry out, it goes to carry in, carry out goes to carry in, carry out goes to carry in, until right here at the last one where we just have our carry out wire. Here it is. It goes to nothing. Yeah, nothing right here. So if you wanted to, you could wire this up to an LED as well, and that would be your signal for overflow. What I want to do with this is I want to make a computer using discrete transistors, and that would require much more than this. A computer has many different parts. Just composing the CPU alone, but this would be part of the arithmetic logic unit, and I can add these XOR gates will allow subtraction using 2's complement, so then that will give us 2 things we could do with the ALU. Normal computers like this one right here, or just any other one, would have other instructions as well. You can see your phone, it has different instructions. The computer is CISC, so it has more than the RISC architecture. But this would be fairly basic more than all of them. What I could do is I could add, you also have you could do just it's a plus b, a minus b. You also have other operations you could do, just as a and b or a or b. Your just logical operations on all the bits. You could do those as well, and I will probably make separate hardware for those as well. So that would compose the ALU of my computer that I'm building. And then of course you have other aspects, a program counter and a bus, and well, you'd have memory registers. And what that will do is that will turn this into a sequential device rather than a combinational one, because right now all of this is combinational logic, and that means that it doesn't have a clock. So if I just turn it on, it just stays like that, and it doesn't really do anything. It just stays here, and it's until I flip the switch, it's not doing anything because there's no clock signal. The clock signal would be for a computer like this, it'd be 1.4 gigahertz or something. Desktop processors go much faster than that. For this one, once I get everything built, I probably do like a kilohertz max, which is very slow. But of course, that's one of the problems what you get when you're doing a computer using discrete transistors, is that it would be slow, just because the speed of light is finite. And when you're going to billions of cycles a second, that does matter. So anyway, here it is right here. This Arduino is just being used to power it. It doesn't seem to use a lot of power right here. But once, of course, if I add the other parts to actually make a computer, it would have a clock signal, and that means that it'll be turning on and off a lot faster in various sections, so it might need more power. I'm not sure at this point. So there's just an update about what I'm working on. One thing I do like is these ribbon cables. These have 10 wires in them, and that's perfect for 8 bits of data, a ground wire, and a plus 5 volts, which is what this runs on. If I haven't explained before, these transistors are 2N2222 transistors. They are NPN transistors. They are BJT transistors as well. So they have a 5 volts of logic, if that makes sense. So yeah, another thing right here is this display. Well, binary numbers can be fun. They're kind of a pain to read, if I would be honest with you. So what I want to do is I have to build a 7-segment decoder, and that will allow me to use a 7-segment display with this circuit. I have some 7-segment displays. Let me see. Oh yes, look, 7-segment display. Oh wow, 7-segment displays, aren't they fun? So what I would have to do is I would have to have a 7-segment display, and that would have an 8 bits of data to, well, it wouldn't be 8 bits, it would be 4 bits to 7-segment display. That would be a decoder, but before the decoder, you would have to have a binary to BCD converter, just because there are so many LEDs that you can only have each one of these 7-segment displays can count from 0 to 9. So that is it's not a binary system. So you would have to have a binary coded decimal that would change it to 4 bits of data, which would go from 0 to 16. Really you could do a hexadecimal with that as well, but if you just wanted to do decimal, that would make it would just go from 0 to 9, and then after that it would go on to the next one, the next place value. So that would require a lot of circuitry. I need to explain that properly in the next video. I know I'm going very fast over this kind of stuff. I've been thinking about it for a while, and I just have to get to soldering the transistors together. People generally don't make computers out of discrete transistors. I'm starting to realize why. At least if you're going to do it, maybe make some printed circuit boards so you don't have to solder all these wires together. But that's how it's going. Once again, the demonstration, let's do some more adding together. Oh no. Let's add, okay, this needs to be off. Let's see what 2 plus 1 is. Oh, it's 3, isn't that great? Let's add 4 plus 2. Wow, isn't that 6? Wonderful. Now we could add this is 4, 5 plus 2, and wait, no. 4, not, oh, you can see this is off, so it's not that, it's 7. Yeah, you can see if I add 1, it's 8. So that's no good, it's 7. So this is my circuit right here. I hope you found this entertaining, or at least informative on some level. And I will see you in the next video where hopefully it'll make more sense. See you next time.